the AI leader and NetMind Chief Data Scientist for Huawei, Balázs Kégl, with us. Balázs Kégl is a machine learning research veteran with over 25 years of experience, with an impressive publication list, both in AI and in physics. After his PhD, he worked in Canada as a professor, then in France as an AI researcher in a physics lab, where he gained experience in applying AI to other disciplines. He got interested in the human and organizational aspect of AI when directing the Paris Saclay Center for Data Science between 2014 and 2019. He crossed from academia to industry 2 years ago, and today he leads a team of 15 researchers at Huawei's Paris Noah's Ark AI Research Lab. So, Balázs, what a pleasure to have you with us directly from France to the world. We're very, very excited to have you here, and very much looking forward to your presentation.
Okay, thank you, Jose, and thank you for inviting me. So I just switch on the slides, which happens to be...
Looks good.
Yes. Okay, so thank you everyone for having me, and thank you for inviting for this talk. As Jose said, I'm originally an AI researcher, so I thought that I could give you a view of all this automation within businesses from the researcher's point of view, the data scientist's point of view. So who am I? As Jose said, I've been doing research for 25 years on AI. Started when I was 25 in 95. The community was like 500 people in the world. Now we are like 500,000. So it was a big change in the last 10 years. I crossed over to industry from academic research recently. But even before that, I was at CNRS, which is the French Public Research Institute. I became interested in the human processes behind AI because I was the director of the Center for Data Science, where our mission was to connect AI technologies with other sciences, so put machine learning pipelines into astrophysics, economy, chemistry, or a lot of other domains. And I figured out that most of the time the problem was not technological, but organizational. At the same time, we started to consult, and I saw that in industry, the problems were very similar to what we had in academic research. The bottlenecks were organizational and management. So in 2019, I decided to join Huawei because I wanted to get my hands dirty and try all of the things that I discovered during those 5 years in a real industrial setting. So right now I'm leading a team of 15 researchers in Huawei's Noah's Ark lab. Noah's Ark is the AI lab of Huawei, and I'm the head of the group in Paris. So it's essentially research scientists, research engineers, PhD students. We are partly doing AI research, but we are facing BUs. So we are solving the AI problems for BUs. So I'm getting into this interface with BUs. The main research objective we have is to build AI autopilots for engineering systems. So my group is on the network BU of Huawei. So we're not working on the phone, which means that most of the things we deal with are engineering systems. This can be software that run the mobile network in the mobile antenna. This can be data centers where we are controlling the cooling system, or it can even be the Wi-Fi network. So there are parameters to set so the connections are the best. And we want to do AI for improving these systems, making them better, cheaper, more reliable, safer, or more energy efficient, which is a big part of what we do. So I will basically talk about how to put AI in engineering systems with a little detour into more general question of how to organize the data science ecosystem in a big company. So I will be going back and forth between these two topics, actually. So first, a lot of you might have known this big result in 2017, I think, when AlphaGo, so Google DeepMind designed AlphaGo, which beat the Lee Sedol, who was the world champion of Go. That happened actually 20 years after Kasparov was beaten by Deep Blue. And it was a short period of time. Actually, all the predictions said that Go will be solved very, very late. And the reason it was solved so fast is because we figured out how to put AI into this system. So Deep Blue, the chess champion, did not use any machine learning. It used a rule-based system. And AlphaGo was completely designed based on learning. So it was learning from games and it was learning from playing against itself. And this was a big breakthrough because it showed the first big result on a sub area of artificial intelligence, which is called reinforcement learning. It's essentially putting AI into dynamic systems, putting AI into control. So the natural question you can ask, okay, if we can solve such a complex problem as Go, why aren't these advances are already in engineering systems? Whereas engineering systems, you could imagine them as much less complicated games that the AI systems should play. The question is even more interesting given that everything is engineering systems. It's 10 trillions of dollar business per year. So if we can just improve 1% of the efficiency of these systems, that's huge money. So there should be a big incentive to improve these systems. Yet we don't really see these algorithms in engineering systems. So why? So let's have like an abstract view of what an engineering system is. You have a system that produces system states, observables that are observed by the engineer who is controlling the system, the pilot. So you can imagine the plane as the system and the pilot as the engineer. The pilot also observes performance indicators like speed, how far am I from where I'm going, or how high am I? So indicators that tell you how well I'm doing my job of controlling the system. As an engineer, I'm also tuning some of the parameters time to time, and the goal is to optimize the performance indicators or at least keep them within limits. Okay, so I want you to have this abstract view of an engineering system in mind for the rest of the talk. So we have a lot of automation already, but if they exist, they are based on deep understanding of the physics of the system, not on learning the system from data. Sometimes it goes wrong. So this is a system that you might know. It's the control room of Chernobyl just before the explosion. There are a lot of automation in this system, and there are human operators. And you see that even when there are human operators who make decisions, things can go very, very wrong. But most of the time it works. Like a lot of manufacturing pipelines are automated. It just doesn't learn. The automation is based on knowing the system and programming the system, so it does it automatically without human interaction. But it doesn't learn either from mistakes or doesn't learn in terms of getting better at what it's doing. So what is artificial intelligence in this context? Because you can talk about AI in a lot of different domains, but in controlling engineering systems, what you want to do with AI is to learn the system behavior based on historical data, and they use this knowledge for improving the control, the performance indicators. So this is the introduction of what engineering systems, what you want to do with AI in engineering systems. So now let's go in a little detour into a more general subject, which is how do you put data science into your ecosystem? What is the data science engineering ecosystem? What are the roles, the tasks, and the work process? So we designed this, or we had this picture when I was the head of the Center for Data Science. So this diagram is describing the scientific ecosystem. The two bottoms, so on the bottom you have tool builders, engineers. So this can be, you can say this is IT in a company, and the data domains, which in scientific domain, it was different, what we call domain scientists, astrophysicists, doctors. In the businesses, that's the BU. So that's like what you see in the bottom are the classical setup in a business. You have software engineers in IT, you have domain experts in the BU. So once you start doing data-driven stuff in the company, the top will appear. So we will have data scientists, and you will have people at the interfaces. So between data science and software engineering, you have this role called data engineer. This is a little bit better known than on the right-hand side. These are the people who are at the same time software engineers and the data scientists. So they know how to put the solutions that data scientists design in the IT of the company. I will not talk about the left-hand side of this diagram. What I will talk about is the right-hand side, because from an organizational point of view, that's the more interesting thing. That's where the value is created from data. So you see three roles there: the domain expert, the BU, the data scientist, and between them is role what I call the data value architect. That's like probably the most obscure role, and where we talk about it at the end. So first, let's meet the data scientist. So if you're coming from a BU, the closest role to this may be business intelligence. But what you should know, and what I would like you to understand, is how we work. So I'm a data scientist / AI researcher. I can do both roles. And if you want to integrate these people in the flow, in the workflow, you have to understand them a little bit how they work. So a lot of people say, why we call data science? Why data science? In my mind, actually, this is one of the roles where is the word science has the most role to be there. Why? Because data scientists actually iterate the scientific method daily. They formulate hypotheses, they collect data, or they look at the data they have. They run a lot of experiments to validate their hypothesis, and then they iterate this. It's a lot of trial and error to build AI systems. So we are actually iterating the scientific methods. We are like doing this science like 4 times a day. If you look at physics, they do it like every 20 years, big experiment. Data scientist does it a lot of times a day. By the way, the person who you see on the right-hand side is George Stephenson, who is the inventor of the locomotive. And that's, for me, it's a good metaphor how you should imagine a data scientist today. This is industry 1.0, perhaps, where we didn't have pipelines. Things were created in the workshop one by one with specialized tools and people who were what I call full stack. So there were little specialization. They built the locomotive from the beginning to the end. Funny thing is that George Stephenson here works on a model train, and what we work on as data scientists are what we call models. It's predictive models, try to predict what's going to happen. We work alone or in small teams mainly because in the work process there is not much specialization and the interfaces are not very well figured out yet. So most of the time it's small teams because everybody does everything. A lot of times it's a single person, the data scientist, sometimes 2, 3. The last 2 points are very important. We build our own sandbox. So there are a lot of tools, software tools for the data scientists, but at the end of the day, every data scientist have their idiosyncratic workshop. And we hate operational constraints. We are little scientists who like to work in their workshops. We don't like standardized tools. If you want to chase away your data scientists, the best way to do it is to give them graphical user interface tools, because we hate them. So just to give you an idea how our workshop looks like when we are sitting in front of the computer. I'll just wait for the slide to change. Okay, so this is what you see. On the right-hand side, you see what we call a model. The model is just a piece of software code with a special API. And on the left-hand side, the black screen is the experiment that's running. with some metrics that we are trying to optimize. Okay, and this is very, very far from what even a person in business intelligence works with those tools like Excel and graphical user interfaces. So this is a typical screen of a data scientist. It's very, very, very bare bone, but this is what I like because it's very, very flexible too. And since AI is an experimental early phase science, we want to be flexible. So this is the data scientist. Now let's see the domain expert, which is in our case in Huawei is the systems engineer. Is the pilot. It can be a pilot of an airplane, although Huawei doesn't work on airplanes, but it can be a pilot who drives like a data center cooling system, or somebody who is sitting in front of a computer and tunes the mobile software so the users, the clients are served well. So the main responsibility of systems engineers is safe operation, not performance. So that's important to see. Performance is important, but it's secondary. The first thing is not to crash the system. And it's true for a lot of engineering systems. And the third point, which is important from the point of view of getting AI into the systems, is that the systems engineer has very little incentive of collecting data and let the data scientist experiment. And the data scientist wants to experiment because AI is about learning from data, and it has to go through trial and error. So the challenge is the following. The systems engineer in this context is not only the consumer of the AI. So the systems engineer will be the person who will work with the AI once the AI is implemented in the system, either as a decision support tool or maybe semi-automation. So there, for sure, there should be interfaces built between the human engineer and the AI. But while building the systems engineer is also the collaborator of the data scientist. So this is very important to understand from an organizational point of view, because if you don't get it, then you will not be able to develop your AI in your company. So the question is, can they work together? Because they have to work together not only when the system is developed, but also in the development loop. And to see you the difficulties, I'll just show you a not so imaginary conversation between the data scientist and the systems engineer. So the systems engineer comes to us, data scientists or research scientists, with a request. I want to use AI. I heard about that. It's so good. Beat the Go world champion. I want AI in my system because I want to be better at it. And I want to actually, as at Huawei, sell hardware to our client with AI inside. Okay, so I really want you to implement AI in my engineering system. So then I asked the systems engineer as a data scientist, okay, can I access your system with an algorithm that I've been developing, which will take control of the system? So it will, you can look at it, but this is the algorithm that controls the system, and while learning, possibly breaking the system. And this is the big point. This is where the system engineer says, over my dead body. So dead end. This doesn't work. Second question, okay, I cannot learn in the system, but maybe you can give me a simulator of the system on which I can learn or can experiment with the algorithm. It doesn't matter if I crash the simulator. And for example, for airplanes, there are good simulators on which we train not AI, but human pilots. But most of the systems, this is very hard because these simulators should be built on first principles, which are sometimes unknown or very complicated to understand. So this is why we want AI, because we want to learn them from data. So the answer we get most of the time, yeah, we will have a simulator, we are working on it. But in any case, it's going to be some simplified thing. So it will never be good enough to be trusted. So even if I show that my control algorithm works in the simulator, I will be reluctant to put it on the real system. So that's an avenue which can be followed, but there are bumps on it. And the third one, which we actually following, is the solution is where The idea is to experiment with the system, but very carefully. So I get some data from the systems engineer. I learn some control algorithm. I give the control algorithm back to the systems engineer, but I keep the control there. So the systems engineer can decide whether to follow the algorithm or not. So the control will stay at the systems engineer, but we can still experiment with the system very, very carefully. And the key here is that I will ask the systems engineer to log the system variables anytime there is something new he does or she does, so I can learn from it. So this is the avenue we are following. So from a abstract sort of like analysis point of view, what just happened there was the following. Normally, I mean, tech transfer, R&D is not new. We have been doing it for 100 years at least. But most of the time, the way it happens is that the systems engineer specifies a problem, gives it to the scientist solves it, delivers the technology, and the systems engineer implements it. Whereas data science is an iterative process because it's data-driven. So there's an iteration where the systems engineer specifies the problem. We are already very happy if this problem is well designed or well described, but let's say it is. Then the data scientist describes the data simulator or the system that she needs. They design the tools to collect and annotate the data and the interfaces to the AI algorithm together. And the data scientist then designs the algorithms, the pipelines, the AI experiments, the metrics with which he works with. And then they iterate, because most of the time it doesn't work the first time, right? So who manages this? It turns out that the best projects I saw, there was somebody, which I call the data value architect, who manages this. So there's a person who designs the problem in the first place with the BU and the data scientist together. So it's a person who understands not only the business needs and the business processes, but also somewhat the data science process. And that's things like breaking the vicious cycle of what I call no data without value, no value without data. Data is expensive, so to invest in good data collection, we have to show some value to the business unit. But to get this value, we need the data. So that's a vicious cycle that is usually broken by doing small pilots and then bigger and bigger pilots. So classical risk management. The other big task of the data value architect is change management, which is not a technical role at all. It's more like an organizational role, because it turns out that most of the time, to accept AI in your process, you need to change how people work. Okay, so for the last couple of slides, we will go back to the engineering system, and I show you the big picture of how we are implementing these principles to put AI into engineering systems. So what you see on the left is the loop that I showed in the beginning. You have the system and the systems engineer. The red arrows are in the computer, so these are APIs. And the purple arrows are the project management steps taken by the humans. So on the API side, what we need to add is a way to log the system. As I said in the beginning, sometimes it happens for legal or security reasons that the system variables are logged, but this data is usually not designed for feeding it into AI. So we have to design data collection on the system. Once this data set is created, so this typically contains timestamps, the control actions that were taken by the engineer, the system observables that describe the state of the system, and the performance indicators. So these are all of them are several columns, and it's usually just an Excel sheet. So this data set is then communicated to the data scientist, who will, based on this data set, design a controller, which should be safe and should be better than the control policy that the systems engineers did for collecting the data at the first place. So this is where we do research, how to do this controller. Once this controller is done, we give it back to the systems engineer, who will repeat the cycle. And the systems engineer will keep the control of the system. So if the artificial controller we gave them suggests control actions that the systems engineer thinks it's bad, they can overwrite it. So that's a very important part for safety, unless we can do it on a simulation. So to complicate the picture, and this is actually sort of like the state-of-the-art diagram we have, is we complicate a little bit the side of the data scientist. What we design is not only a controller, but also what we call a stochastic simulator. So we will actually learn simulators of the system, which what do? They predict, they anticipate how the system will react to certain actions. And the reason we do this is two things. First, we'll have a simulator. So on that simulator, we can safely try any control algorithm we want. And second, the simulator itself can be an output of this project. We can give it to the systems engineer. They will be usually happy with it. It's like designing an airplane simulator just by observing how the airplane reacts to pilot's actions. As I said, most of the time, these systems do not have a first principle-based, physics-based simulator. So these data-driven simulators are also output of the project. So these are the two reasons why this sort of algorithmic setup or modularization is good. What we found very, very interesting, and this is where my researcher side kicks in, is what I'm really interested in is to drive research so that the output of the research can be inserted into the work process. So the algorithms we develop have to satisfy the operational constraints in which they will operate. And so we were very, very happy to come up with this diagram, because this diagram, I believe, can be implemented within the work processes of the company and can drive research in terms of, like, we have to fill those boxes out, how to make the controller, how to make the stochastic simulator. So this is what my research team is actually doing after figuring out, how we can be useful for systems. So just to really dive in to the kind of things we do, what you see on the right-hand side is one of the system observables. It can be a KPI or it can be just a system state. The red part is the past. At step 18, that's the present. The black one is the real future. So these are either simulators or observed data. And our goal is to stop at 18 and try to predict what's going to happen. So the orange curve that you see is the output of our algorithms that tries to predict the future. So you can also think about forecasting like meteorology, where you want to predict the different temperature paths 1 day, 3 day, 1 week ahead. So once we have this, then we have a simulator and we can design our control algorithms. So this is the big picture of what we do and how we implement the principles of AI organization within this framework. And so this is my last slide. So we are going back a little bit to the abstract level. This would be my recommendations for any company who wants to delve in AI and who wants to put AI into work processes. So first, you need a strong top-down mandate. Usually CDO, CDSO positions are not very strong, usually put close to the IT, whereas in my mind, that person has to be strong because it will have to impose changes on how the BU works and has to impose constraints on the data scientists. So without this position, either inside the company or by talking to consultants, this will not work. The second recommendation is to form commandos. So if you talk to consulting companies that do this, most of the time, 70% of the project is not technical, it's change management, because AI will have to be adopted by people who work, so it's like a work tool. The 20-10 is the data science of 30%, where 20 is like data cleaning and only 10% is what we call purely data science. So that's an interesting thing to note, because the commanders have to have people who are not technical but organizational experts. The third one is to build trust through iterative pilots. This is not something that AI invented. We have to start small because we have to show value, so we can have funds for data collection and building the pipeline, which is an engineering problem. The fourth one is to design a data science process. So that's the idea of moving into a sort of standardization of what the data scientist does. You will see a lot of resistance from the data scientists because, as I said, we like to be very, very free. But in the long run, especially if you have more than one pipeline to implement, it's a good idea to start having a memory and standardized tools that the data scientists use. And I have a blog post on this if you're interested. And the last one is the continuation of the fourth point, is that we need to start building standard operational tools for data science, which what we have are basic, very bare bone, low-level tools, but not operational tools. So what I mean here is like pipelines, things that are standardized. So we are actually using an experimental software library for this within the team that I'm trying to push also to the BUs, because the idea is that we use the same tools for doing the experiments and the BU uses the same tools for productionalizing the pipelines. And so with this, I'm finished. So thank you for listening to me. And I'm opening the floor for questions. So I will stop the slides and give the mic back to Jose.
Thank you very much, Balázs. Great coverage of of artificial intelligence, specifically on the applications on engineering systems. I think that's quite interesting. I've had the privilege of leading a very large transformation for an organization with 12,000 engineers, interdisciplinary, and very aware of the applications that you're talking about there and the challenges of, I always told people, it's a place filled with ideas and 12,000 different opinions about anything, because
yes.
Engineers will sit there and talk about, defend their point of view on a certain aspect of an idea for a very long period of time, and it's both very exciting but can be quite challenging. So I'm glad you're focusing on that. The first question that has come up here is a bit of a more general question. Since you have such an expertise in artificial intelligence, if you look back in the last, I think most people now have caught up with what happened with Go and the deep mind work that has taken place. If you look back at the last 12 months, 18 months, has there been other advances in artificial intelligence that you think are noteworthy that we should be keeping tabs on?
So my domain, which is reinforcement learning control, it's a slow-moving domain. We had big breakthroughs, but right now it's a lot of like small steps to move towards something that's robust. So most of the algorithms we are working on can work very well. Sometimes they do beat the world championship, but sometimes they do very dumb moves. And robustness is, in a certain sense, more important than performance on the average. But if I go out of this subdomain of AI, the biggest breakthroughs are in language processing. So right now, the big IT companies like Google, Facebook, Amazon, they have the computational infrastructure, they have the data to feed basically all internet into language models. So the keyword, if you want to look for it, is GPT-3, which was developed not by Google, not by Facebook, but by OpenAI, which is a company that was founded by or funded by Elon Musk, and they did this. So it's a lot. They burn a lot of computer cycles, but at the end they have a language model which is very, very tricky. Sometimes it writes an essay that sounds like comes from a philosopher, But sometimes they still do very strange mistakes because they don't live in the world, they live in language. So it's a very interesting advance. It feeds into the bot industry. So a lot of companies now can interface with GPT-3 and design their own language bots. But I wouldn't trust it with things where I need safety, like, or understanding the world on the basic level that any 6-year-old child understands. So it's a very interesting thing because sometimes it's very, very sophisticated, but sometimes it just makes dumb things, you know. But that's for me, that's the biggest advantage, the biggest breakthrough in AI in the last 2-3 years. Yeah.
Very good, very good. Marla Vanessa Zuniga has a question for you. She is asking, you know, Huawei of course has developed applications probably on the consumer segment and industrial segment of its technology development, if you will. How does that work for a research group like you and with a company like Huawei in terms of the collaboration for developing, you know, artificial intelligence algorithms? Are some of these consumer applications or industrial applications helpful and useful for you in the research work that you do, or you're tapping maybe other external sources for that development?
So we are working at least half of our time, but even more for BUs. And Noah's Ark, which is a lab of about 500 researchers, we cover all the space of Huawei products. So there is a big part of Noah's Ark who works for the phone. The most successful AI applications are in pipelines where the pipeline is well defined. Like we know what we want and we know how to measure what we want. And so for example, Huawei is a leader in photo enhancement for the phone, or 3D, or you know, low light photo enhancement, because there we know what we want. We have like low light photo, we take another photo with a better camera which has a highlight, and so we just want to match the two. So and in these pipelines you can have you can develop the research cycle that delivers very rapid results, because this is what researchers are trained to. There are other pipelines like this also on the network side, where the problem is well defined. Like, I don't know, in a mobile tower, we want to know which packet is coming from which type of application. So if it's video, if it's video phone, or if it's just somebody browsing, we need we can set the best parameters for that kind of application. And that's again a very nicely designed pipelines where we know how to measure the performance. So the way we work is sort of like, or any data scientist actually in a big company is trying to go for the pipelines where these elements are already there. So what's the output you want from the input? Do you have data? Somebody annotated the data, and I can measure how well it works. So I can do the cycle of improvement. The trouble comes when this is not done, or when this is hard. So it's not done not because somebody didn't do it, but it's genuinely hard. And in a certain sense, that's what I'm most interested in, how to improve this process and get into domains where figuring out where the value will come from and how to measure that is hard. So I don't know if I answered the question, but these are my thoughts around this.
No, you provided some very interesting insights there. The question was about advances in technology and maybe how they cross-pollinate from consumer applications maybe to more industrial or engineering applications. And as a matter of fact, there is a number of questions around this theme, and I'm gonna have a little bit of fun with it. I'm gonna ask you this question.
Okay.
It's a bit of a sci-fi question as well that people are posing on the chat right now. And the question is about general AI, right? What, of course, a lot of this, and this is interesting on the context that you explain, where a lot of engineering systems type of innovations and improvements, they require very domain-specific knowledge, which AI could be useful for that. but they also
Mm-hmm.
require a lot of interdisciplinary multi-domain knowledge, which
Mm.
makes applications quite challenging because we don't have a general AI model yet. What is your assessment from a research standpoint? Is general AI an inevitable progression that we're going to have to, or it's really not like that? It's more of a discontinuity on the curve, and you're going to have, it's not a natural progression of the advances in AI we have today. It will have to be a breakthrough of a different sort. So curious from a researcher standpoint, how you see the development of AI and specifically moving towards a generalized AI model.
I don't think anybody knows what general AI is because we don't know what intelligence is. And either it's something very reductionist, where we get into a domain and where we can measure the performance. So we know that it's like image recognition or speech recognition or language understanding, where we design those metrics and we have the pipeline and we call it AI and it's particular for that pipeline. Or we're getting to almost philosophical questions about what AI is. So I think the question is a little bit overblown. At least I'm not that much interested in the question. I think if we get to something like general AI, we will need at least 2-3 big breakthroughs as big as we had in the 2010s on deep learning, if you know the topic. That must come from or areas or research areas which are completely under the radar today. So it's hard to predict them because as deep learning was hard to predict in 2000 and everybody was not a believer in it, I think the next breakthroughs are also unpredictable. And it's very likely it will not come from the domain of deep learning or neural nets, but from somewhere else. I have a vision about which direction to go, and it's related to what we're actually doing on systems. We need to design systems that live in the real world, not on the internet. I don't think we can design AI by just looking at images and reading text, because it's going to be very, very witty, smart in a certain sense, but very dumb in another sense. So we need robots, we need systems that actually, grab stuff like we do and have goals. But I'm not claiming that this will lead to general AI. And yes, so probably I disappointed the questioner, but I will not do anything. I will not say anything else about it.
No, that's good. That's good. We have your perspective and experience there. I think, of course, that is a topic that we can spend hours discussing. So let me move on to the next one. Let's talk about one of the themes that has come up. A lot of people in this, the audience here have over 2,000 registrations here, and business transformation leaders, operational excellence leaders, and a lot of engineers and scientists are listening to us as well. And one of the themes that has emerged, and as a final wrap-up question here, is the big data versus small data, challenge. And I'll give you a very specific one. I was leading a major innovation project for a very large energy organization, and we're looking into finding ways that we can remove mercury from emissions, more effective ways. And we had a very big, complex machine that was designed to do sulfur dioxide removal, and we're trying to make adaptations and to remove mercury as well. In any case, this is a very complex system, and then we asked for some data to be collected, and we got 18,000 data points on this machine. But after looking at the data points, and we know this is not AI, this is just like multivariate regression analysis, just really trying to understand the key drivers. And after looking at it, we realized that, it's good, but we don't need 18,000 data points. We would be better off with 8 data points, but the right data points in operating conditions that you normally don't run, because of course, when they're running the machine, they want to keep a very tight control. So there is this challenge that if you learn by observing operations, you're not going to have a variation of the inputs that will teach anything very valuable about how they affect the output. So the question is, big data versus small data. There's a lot of talk about using big data for AI. Can you tell us in a minute or so what's going on with small data, high quality data in AI? Is that an area that we can use AI or not really?
Well, you just touched the question we are brainstorming right now, so it's very interesting. All the data we have here is small because engineering systems are not getting faster with time. Computer systems or CPUs, GPUs, they get fast. There's the Moore law, but the physical systems that we are studying are on the same clock. So the data we collect is always the same size and usually small. And the other question, for me, it's even more interesting is this control question, is that all the data we have come from systems where the engineers try to be very good and robust. So they always do the same thing in the same state. So it's very hard to learn from this data because they never change their control policy. So one of the big questions we are studying is how to give algorithms that explore the space carefully. So we sort of learn what the engineer does, and around that a little bit of randomization, so we can discover the regions where we can improve the algorithms. And this is one of the biggest questions for us, if you want to apply this. And one of the questions, it is studied in research. I'm not saying it's completely not studied, but it's not the focal point of AI research. So that's the big paradox. The AI research is on big data. It's getting bigger and bigger data, putting on bigger and bigger machines, and on pipelines that are known, like image recognition of NLP. But this question of like having methods for heterogeneous systems where I can just take the method, put it on the system, and it learns by itself, we are very far from it. And so it's a very good question. I don't have an answer to this, but this is what we are studying now.
Fantastic, Balázs. Those are some of the real challenges, I think, in the research going forward. The kind of combination of design of experiments with AI development is fantastic. Listen, we're out of time, unfortunately. We could talk about this for hours. I'm very, very grateful for you to take the time of your busy schedule from Paris, France to the world, share your insights about the developments of AI in engineering contexts and industrial contexts, which are quite interesting for our audience. So thank you so much for doing that. We had a lot of fun just learning with you today.
Okay, and thank you very much, Jose, for inviting me. It was a pleasure to talk to you guys, and I'm looking forward. You can contact me on LinkedIn or find my mail, and I would be happy to share insight. Thank you again.
Thank you. Ladies and gentlemen, that was Balázs Kégl, research leader for Huawei, directly from Paris, France, and tremendous insights on how artificial intelligence is being used and the challenges of its usage in engineering systems in industrial settings. Terrific insights. Our next presentation at the top of the hour will come from Donald Cook, who is rapidly transforming enterprises through RPA and intelligent automation for this virtual post-COVID economy. Donald Cook is a global leader and senior executive and advisor for many leading global organizations on this topic, on how you build intelligent automation on social and industrial practices. So you do not want to miss that. He is a speaker at the World Economic Forum, and just tremendous insights with decades of experience and application of high technology. So we're going to see you back at the top of the hour with Donald Cook on rapidly transforming enterprise through RPA and intelligent automation. See you soon.